So, hello and welcome to Prague Mathematical Physics Seminar. Today our speaker is Josef Svoboda from Miami University, and he will tell us about the Z not invariant, Z0 invariant, and splicing.
Yeah, there are two universities in Miami. One is University of Miami, and the other one is Miami University. So,
so you are from
the University of Miami.
Okay, sorry.
Yeah. We just did the don't get. So I will talk about this Z0 not invariant and so-called splicing. So first, I will start with a bit of some history and motivation. Why study this? Then I will talk about what is this Z invariant. There are many flavors, but it's basically all some Chern-Simons path integral with various mathematical definitions, because it's not easy to define it. Then I will talk about plumbing and splicing. So those are some classical constructions in three-dimensional topology. So this is a 3D invariant. And finally, I will present some say new results and conjectures. Okay, so I don't know the history very well, so this is my interpretation. But so why people started studying three-dimensional topology? So one reason, and I think it was the original one, was that they were actually studying algebraic equations, and Poincaré considered this famous equation, x squared plus y cubed plus z to the 5. And if you take solutions, so this is in x, y, z are triples in C3, and you consider triples such that the Euclidean norm is equal to some small epsilon, then this is real dimension 4, this is real dimension 5. So if we intersect it, it's in transfer, so we get a free manifold. So we get a free manifold. And this is a very nice free manifold because it answers one of the one various questions, which was whether there is a manifold which looks like a sphere, but it's not actually a sphere, because this manifold, which I'll call Y, I'll try to call three manifolds Y, satisfies this condition. So satisfies that if we look at the homology of this manifold, which is the basic algebraic topology invariant, then it's the same as homology of three sphere. So this would be the most naive Poincaré conjecture, which would be saying that if the homology or cohomology is the same over integers, then the manifolds must be homeomorphic, but they are not, they are different. And the reason is that phi 1, the first fundamental proof, has 120 elements, as can be computed easily by the Fun and theorem. So this is a good exercise for some students in algebraic topology. I never did it, but yeah, it's pretty straightforward. Yeah, so you can write the presentation of this group in terms of these numbers here. Yeah. So this is this is the beginning, and then after this, people started asking if they can find out other examples with this property. This got a name. So this is a definition that y which satisfy this. Satisfy this condition is called the integral homology sphere. Sometimes people omit this Z and just say homology sphere. Homology sphere. And I also want to consider, so there is also a version with Q, which is also important. So if it satisfies this, then we say it's a Q homology sphere. Or basically for any invariant group, you can consider this. After people started studying this, then they realized that there are really many homology spheres and many rational homology spheres. And there are there are some constructions how to pull them together. For example, if you take connected sum of two homology spheres is another homology sphere, but there are also many irreducible ones. Yeah, so nowadays there are many ways how to compute, how to find homology spheres, and you can think about them as some kind of simplest three manifolds because there's no homology. Of course, there are many other three manifolds, but this talk will be mostly about these rational homology spheres where some like kind of combinatorial techniques may be used. Okay, yeah, and so one way how to study these homology spheres is the famous Casson invariant. So this is still in the history part. So Casson defined invariant lambda, which is defined for homology sphere. So Y must be a homology sphere. So Y is Z-homology sphere, and then it was extended by Walker to two homology spheres. And this has something. There is a choice of a group. There is a choice of which is SU2, and this Casson roughly counts representations of phi 1 y to SU2. There is a precise definition which is more complicated, but this is the idea that we are counting the representations of the fundamental group. So, for example, here for the homology sphere, you will get something which is different than for three sphere. So it distinguishes them, and this Casson invariant distinguishes many homology spheres. So that's why it is important. Yes, and in a sense, it's a bad invariant for a three manifold. In the precise sense that it's kind of, or maybe not so precise, that it's defined for homology spheres, then you need to put a lot of effort to define it for Q homology spheres. And then you need to put a lot of effort to define it for something slightly more general and slightly more general. It is not something which you define for all three manifolds at once. And it is not a TQFT or anything like this. So it doesn't have these nice properties, but it has some nice properties, but this is like a caution that it's really defined for this small class of three manifolds. So it has one very cool property, and this is related to the splicing, so the second topic. So what is splicing? Again, this is something defined for homology spheres. So if I have y1 and y2, and I also pick knot inside, so I pick a knot inside y1 and pick a knot inside y2. Then there is a canonical way how to glue these two manifolds along these two knots, because I can take these two manifolds and then I have some knot here. I don't know how to draw knots, so I will take the knots and I will remove two neighborhood out along this knot. So I will remove a solid torus, and then I have a boundary is just the usual two-dimensional torus. So I will do it with both of them, and then I will glue these two tori, and because this is a homology sphere, there is a for any knot you always have the small circle around, which is like in the opposite, in transverse direction around the loop, which is the knot, and then there is a canonical longitude around the knot, and this is because of the Z-homology sphere property. So this is something which doesn't work in more generality. So you glue the longitude to the meridian and meridian to the longitude. So there is this canonical way how to do it, and this produces this produces this kind of with this knot produces another sphere. So this is this splice.
It is somehow forced all these surfaces to tori, not solids. The surfaces to tori are glued together.
Yeah,
I cannot choose.
You can choose in general. You can choose like 2 times 2 SL2Z matrix. Yeah. So there are many possibilities, but there is one canonical one in this case. Yeah. So
and this is meant. Sorry.
This is meant, yeah. This is which we take. And if we take this canonical choice, then we have this very nice theorem of Svoboda and somebody else at the same time, that if we take some of these custom invariants, this. It is just simply additive like this. So the splice, the custom of the splice is some of the custom invariants. And this was a good note that you can actually pick a different way of gluing using another matrix. And then if you do it, you would get some additional terms here. You would have to somehow you use them. But in this canonical way, it is really simple like this. Yeah. Okay. This was splicing, and so we see that splicing gives us more complicated homology spheres out of simpler ones. This can get really complicated because we choose arbitrary knots here. So it's really very general construction which generalizes connected sum. And we can also think about the opposite procedure, kind of this splicing, that if we start with a homology sphere, we may try to split it in this way to some easier blocks, some building blocks, and this will play a role in what we'll discuss next. Okay, so this is Casson invariant, very classical one, and now I want to also other invariants. For example, there is Neumann's mu bar invariant is also additive under splicing. So this is a nice property of these invariants.
Sorry, can I ask a stupid question?
Yes.
So this Casson invariant. So you said that it counts these maps from pi1. So does this Casson detect more than the fundamental group, or is it like strictly less information?
So fundamental group is more or less the same thing as the manifold in 3D. I mean, there are some length spaces when the fundamental group doesn't determine but it's more or is the same thing. Yeah.
I see. Okay, thank you.
Manifolds are like group theory in a sense. Yeah. So.
Thank you. Thank you.
Yeah, this is obvious for hyperbolic manifolds because then you can find this hyperbolic metric out of the data of the fundamental group, and for other manifolds, for cipher manifolds, it's a little bit more tricky, and it's described in a book of Orlik on cipher manifolds, where he gives criterion when the fundamental group determines actually the manifold. Yeah, okay. And also, you know, it relies on a Poincare conjecture, because before Poincare conjecture, people didn't even know if the trivial fundamental group means that it's a 3-sphere, but we now know. So probably, yeah. Okay, so let's talk about this invariant. So Casson invariant is probably, I don't know, 70s or 80s or something. And since that, there was a lot of progress on these TQFTs, on many new invariants, on a famous paper on Jones polynomial, and then on Chern-Simons theory. So all these things. So this is, and also the representations of quantum groups. So this is in this realm. So if we consider Chern-Simons, theory for SU2, so we can so Witten wrote this path integral, and then he found this perturbative expansion. So this is one thing which we can study. This is this perturbative expansion, and then we can try to study the true path integral, so non-perturbative series. And this was done by Witten. So Witten, because we defined this path integral, consider the Reshetikhin and Duraev. And I will try to draw this nice picture, which Sergei Rubov always draws in his talk. So this is a unit circle. So here is 0, here is 1, and over here we have various roots of unity. So q to n equals 1, and so this perturbative expansion can be thought like living around 1. I will explain what that means. And then there is this Witten-Reshetikhin Duraev. So this was originally defined as for an integer n. But then people realized that it's better to think about this n as a root of unity. So this is a playful root of unity. And after people, and then there was this famous paper of Lorentz and Zagier, where they considered a function which is defined on which is defined over here, everywhere. And if you take the radial limits to roots of unity, you recover this with energetically derived invariant. So this has something to do with the in the Chern-Simons, you have this level k, and this must be an integer, right? And then people try to complexify it, go from out of the integers. So this is now very well understood. So we have, or at least in many examples, we have a function which is defined on a whole unit disk, open unit disk, and if we do the transfer, if we do the radial limits to roots of unity, we get the usual differential invariant, and if we do expansion around 1, we will get this perturbative series around the trivial flat connection. Okay. So yes. So this Z0 is a function of Q. Q is a lives in a unit disk. And so you can think about it as a complexified analytically continued path integral. And if you do limits to the roots of unity, you will recover the usual well-defined with energetically derived invariant, which is defined using quantum groups. Yeah, and so then there are many other. So there is this zero here. So this zero here is related to the. So we have Chern-Simons action, and there are these critical points which are abelian, so non-abelian flat connections, and then abelian connections play us. So yes, I should say that the flat connections. They exactly correspond to these homomorphisms of E1, Y to SU2. So there should be some relation to Casson invariant, and there seems to be, or at least so Casson invariant appears there in many places. One of them is in this perturbative expansion. So this is like the first term of the perturbative expansion. So and you can expand this path integral around some of these flat connections, and you get many perturbative series. So you have some perturbative series for any non-abelian connection. Then you can use this resurgence theory and get some invariants. So this is any non-abelian. You can get maybe I'll call it B. You get some different series. I also call it Z, but this is now just for abelian connections. In particular, the trivial one. So this is one of them. This is zero, and this is some. So these are formal power series of some H bar, but this is a honest Q series defined in a unit circle, and this has some various contributions from these non-abelian parts. And then a final step is which was done in so this was Gukov, Kuprov, Vafa, and many. I mean, there are many papers on this, and there is Z-heads invariants, which are also labeled by abelian connections. And they are more or less the same thing. It is just that we take these guys and we multiply them by some. We basically just change linear change of coordinates. And these guys have the nice property of having integer coefficients and integer exponents. But basically it is the same thing. We just multiply by some matrix of the number of the abelian connections. So yeah, so I will be talking about this Z0. So this is this non-perturbative series assigned to the trivial connection, and this is the series which leads to the usual return-reciproc interactive into the rate elements. Okay, so there is a bunch of invariants, and also there is this story of 3D correspondence, which assigns to any three manifold 3D physical theory. So there is another source how to get these invariants, which gives us hope that it's really a PQFT like invariant, and yeah. So there is another like theoretic story behind this. So yeah. So for us, it's the most important thing is that there is actually an explicit formula for these invariants. So in the old times, people knew this perturbative series, and they were trying to get this by this hard resurgence, which is very complicated subject. But nowadays, there are many explicit formulas for these Z heads, and this Z0. So this is a special case of this matrix over here is some matrix which is some ones over here, then there are some roots of unity. So this Z0 is just the sum of this Z head over all B. So this is an invariant of a three manifold with a choice of abelian connection, which is or maybe it's better to think about it as a spin-C structure, which is so if we have a three manifold, which is a Z-homology sphere, then we have a H1, a finite group, because of this condition that there's no, because the homology of Y is the same as homology of three sphere over rationals. Mm-hmm. So that means that this doesn't have any Z inside or something, just this finite torsion. So this is a finite group. This is a very important. So Y is Q homology sphere. If this is a Z-homology sphere, then this group is trivial. Yeah, and so the abelian connections are labeled by elements of this group, because abelian connections are homomorphisms from H1, right? So maybe it's like a dual of this group, but it's the same thing for finite abelian group. And there are also spin-C structures which are coarser for this group. So they are non-canonically, they can be non-canonically identified with elements of H1. So from some consideration, it's maybe better to think about this datum as a spin-C structure instead of abelian connection. Okay, yeah. Anyway,
so it is somehow a product connection. I have spin 3 C.
It's a spin-C structure,
which is spin times U1 over Z2.
Yeah, this is like
and then I have this abelian. I don't understand the word abelian. Sorry.
No, I'm talking about this
U1. Yeah. Do U1?
Yeah, I'm talking about sorry.
S2 is the same as spin 3.
No.
It will be okay.
Abelian connections. I just mean something which has a image U1 over here.
Yeah.
Yeah. And this is related to spin C structure, like additional structure on the manifold, because these spin C structures are closer over the first homology. So if you would have like a non-trivial Bethe number, there will be plenty, there will be infinitely many spin C structures. Okay. Yeah. Okay, so this is yeah, and I should write the formula, right? Okay, so to make sense of the formula, I need to say something about the plumbing. Any questions? You don't have to think about spin C structures. It's fine if you just think about Adrian connections. It is really just a technical detail, I would say. Okay. So if we consider, so there is a special class of free manifolds which are called graph manifolds. So these are even much more special, and this is where the combinatorics can be, because they are going to be constructed from a graph. So if you start with a free sphere and you consider a link inside it, so this is a bunch of knots linked together, then there is this dense virtually construction, where you take the link, you remove the solid torus around each of the component, and then you glue inside some tori using some SL2 matrices for each of the component, using the automorphisms of the boundary, which is a torus. So in this way, you can get any free manifold. So in this sense, knot or link theory is the same thing as free manifold topology, because for any free manifold, you can find a link such that using just this cutting and glue pasting construction, you will get this free manifold. On the other hand, if I give you some free manifold like a Poincare sphere, it's not so easy to find this link. Also it is in no way it's unique, because you can do some operations, so-called Kirby moves with this link. You can add components or somehow put them together or remove out of each other. So there are some moves which are described by Kirby, and so for very, very different links you can get the same free manifolds. And this area is called Kirby calculus, and it's very, very hard, because there is basically no way how to say that two links are related by these moves. Even if you are an expert, there can be some very long sequence of moves which you just cannot find. So this is Kirby calculus. But this historically, Kirby calculus was related by Neumann's moves, and this is a special case when we only consider links of other knots. So we only consider like this. Okay. So this is easier. On the other hand, because we have less freedom, actually there are more moves. It's more complicated. But so we take only unknowns, which makes it much easier. We have more moves. And since we have only unknowns, we can kind of forget about them and just write dots for each of the unknown and write an edge if they are connected, like this. So, for example, we can get one pair sphere by considering this famous diagram. 3, 4, 5, 6, 7, 8. And also we need to give, the data of the 2 times 2 matrix. And it's actually enough to give some fraction of 2 numbers in the matrix. So it's a rational number, and here it's -2. So this is called framing. And it's important to give, you need to give the framing to make sense of this construction. Okay, so graph manifold is a manifold which you get from 3 sphere by surgery on length of unknowns. Yeah, this is also called plumbing. When Norman defined this, there is also 4 manifold version. You can think about these 3 manifolds as boundaries of some 4 manifolds. So you can do this on 4 manifolds too. Yeah. Okay. So this is a very simple class of 3 manifolds. In particular, you will never get something hyperbolic because you never get some complicated hyperbolic knots. So this is really like a playing ground for children in topology, but that's what we do. So now, if we have this graph manifold, we can package this data in terms of a matrix. So we take M is adjacency matrix. It simply means that we take a matrix of rank the number of vertices. If 2 vertices are connected, we put one of diagonal, and on the diagonal we put these framings. So this matrix for converse here would be something like there are -2s on diagonal, and then there are some 1s like this. And then this vertex is 3 neighbors. So this is a very famous matrix. It is determinant 1, because the determinant of this matrix is exactly the number of elements of this H1. This can be thought as a co-kernel of this matrix. So this, yeah. So this is why it is combinatorial, because you basically have some lattice which has rank the number of vertices. You have some matrix, and this matrix encodes everything. The only kind of tricky thing is that you can change this. You can add a vertex here with framing 1 and change this framing over here. So those are these Neumann or Kirby moves. So it's not like that the graph, there are many graphs giving you the same manifold. So if you want to construct an invariant of a 3 manifold, you need to construct something out of the graph which is invariant with respect to these moves. So usually people have some intuition what should be an invariant from topology, and then they cannot define it because it's some path integral. So they go back to these graphs and they try to find a formula which kind of should be the same thing, and they prove that it's invariant under these moves. That's how people construct invariants. Yeah, and so one formula which is invariant. Maybe I will write it here because I have Z0 here. So it's okay. So I will do Z. I want to talk about Z0, but this is just a sum of over A of this Z star Z cube. So I'll write a formula for each of these. So this is, okay, there are some boring refactors. So this is a trace of this plumbing matrix, adjacency matrix. This is signature. This, I don't even know what this is, some sign. Also depending on the matrix. Oh, I forgot what this is. Anyway, this is just to make the invariants under Kirby moves working. In many of the papers, they just don't have it there, you know, because they didn't really care about that. When Bubov and Malascu tried to prove the invariance of Kirby moves, they realized that it's not invariant, so they added some, or at least this is how I think it works. Because the kind of the exciting part is what I'm going to write next. And this is, so in the end we want to have a series in Q. So we start with a huge integral over all vertices. We consider a curve integral on a unit circle with some variable zd for each vertex. Then we take zv minus 1 over zv. Yeah, don't expect to get much intuition from this definition. The reason why this is not easy is that this definition is so messy. So there is a factor which depends on the degree of each of the vertex. So this is kind of the interesting thing. This is here in this Lincoln diagram here you will get something interesting because here you have valency 3, degree 3. So there will be 1 over this term. So it will expand as a Taylor series. So that's why we get infinitely many terms. For these guys, there will be just 2 terms. And finally, there is this big sum over this. This is the lattice generated by vertices. Here,
the matrix is chosen.
Yes, the matrix.
Yes,
this is
and
the
notice.
This is the data of the 3 manifold. This is
Okay. And the pi also, they probably.
The pi is just some I don't know. It's like positive definite or negative definiteness.
It might be related to the.
I forgot. It's definitely just something which you read of the matrix.
And then the graph is also connected to the manifold. If you start with the
manifold. The graph is the same thing as the matrix. The matrix just encodes the graph. Yeah. So here we take a sum over lattice, and this is like this is kind of like a so there is some quadratic form here. This is a quadratic form given by this matrix.
M is the matrix.
M is the matrix. M is the adjacency matrix.
So you can really write trace of M.
Yes.
Okay. Yes.
There should be also signature of M. Yeah. And then there is a product of these variables CP to LV. So L is a vector in this lattice multiplied by the matrix. Then you take a quadratic form. You take Q to the quadratic form, and you take product of ZD of the components of the scalar V. Then you multiply by this thing over here, and finally you integrate over ZV. So basically, just take constant term in this thing. So this sounds crazy, but yeah.
This absolute value of ZV should be equal to 1 or epsilon or
equal to 1, yeah.
And ZV cannot be ZV prime if B is not prime.
Those are different
Those are
variables.
different.
Yeah, those are variable for each. So basically, it means that you expand this as a Taylor series to both sides, like a positive and negative, and then you multiply by this stuff, and then you take a constant term. So you actually take some combinations of these variables, C1, C, some monomial like this, and you trade it for some power of Q, where this is like the, this 1, 3, 1 is this vector, and you just put Q to this thing instead of this term. So in the end, there are no Z's there.
There are no.
No Z's, because you integrate over them. The only thing which remains is this Q. Okay. It's really like a messy definition. That's how physicists like to write, because they like integrals. For me, it's not so. I would prefer something else. Yeah, but basically.
So do you get it somehow from Chern-Simons?
So. I mean, I can show you the paper where they like get it somehow, but they also use this alpha vector invariants. Yeah, I don't know. It's like a miracle, yeah, because they really get something which gives you these things to roots of unity. For each of these. No, this is no. Zagier did just one example. This is a group of people to alpha.
Ah, okay. Yeah.
So Zagier did just one example, which is the homology sphere.
Yeah. Okay.
And then they generalize it to graph manifolds. And nowadays they also do some formulas for hyperbolic things, for knot surgeries. But this is still in progress because some, yeah, but it's very active, yeah, writing formulas like this. So yeah, so basically my goal is to understand this formula, and the way how I do it is that I'm very scared of it, so I just put it into computer and I look at this Q series and I guess what is the result. But basically, if you plug in, so maybe I should say, like, for example, if you plug here a graph like this, there are 4 vertices, then there will be some series, but from this vertex here, infinite series, because you will get infinitely many monomials, and then you trade them for some Q to something quadratic. Yeah, and there will be also there will be 8 of these series, because for each of these vertex you have 2 factors. Yeah, so it will be like sum of 8 things, which are some kind of functions of yeah. So
this is spin 3. Yes, so the plugin linking of spin 3.
No, this can be any polygram with any frame. So this is like yeah. This is the similarity with linking diagrams is just that if you take linking diagrams with -2s, you will recover the links of ADE singularities. Yeah. Yes, it's much more general. Yeah. Okay. How much time do I have?
Time 15 minutes.
15?
Yeah.
10, 15? Okay, yeah. So yeah.
Or do you need more?
Yeah, that's fine. So this formula is around 2017, 18. It's still kind of new. And that's also why I it's kind of fully understood.
Okay, sorry, I need to already obtain the sum of 8. You didn't mean product of 8 elements.
What are you talking about now?
You said
no, it's sum. Yes, sum of 8 series.
Yeah.
So I will say how it is for Poincare sphere. For Poincare sphere, you will get so yeah, I need to say what is the false theta function. So theta function is something which is something quadratic in Q, and it's a series. So this is sum of Q to n squared over 2. Here I will write some p. P is an integer. Positive integer, and here we take sum of n incongruent to some class modulo 2b. There should be also some sign. So this is a false theta function of modulus p and the residue class a. Okay, so you take infinite sum. This is all over all integers. There is some quadratic term in Q, sorry, and we only sum over some residue class. So if you do this, you will get some combinations of this size. There should be 8 of them, and so they have modulus 30, and there are some numbers. There are some. Or more. So you have this was done by Lawrence and Zagier, this example. So you can think about this, some functions coming from number theory, or if it's interesting for number theorists, and suddenly if you take a radial limit, you will recover fit energetic integral for some manifold. So it's a full connection. That's why I mean Zagier always says that that 3 manifold topology is actually number theory because since on each manifold you have some nice metric, it's very rigid, right? So it's like having close to number theory. There is not much room like in the higher dimensional topology. Okay, so this can be written as this combination, and yeah, somehow in the literature it was always kind of mysterious. What are these numbers here? How to, even though there is an explicit formula. So I have now like a conjectural formula which works for Seifert manifolds. So Seifert manifolds are guys which have star-shaped graph. And they can be, so the Seifert manifold can be described in terms of so-called Seifert data, which is a bunch of fractions. And this is a special kind of manifold which fibers over a surface. So here is S2, here is this manifold. And it's almost like a circle bundle over S2, except that there are some so-called singular fibers. So these singular fibers can be described by kind of like monodromy around them, and those are these rational numbers. So these are very special kind of manifolds, and very well studied. Everybody studied Seifert manifolds, and they correspond exactly to this graph manifolds where you have star-shaped graph. The number of legs is the number of these singular fibers, and the numbers on the legs are given by the continuous fraction expansion of these numbers. So this is where some little number theory already comes into play. Yeah? So we need to write this Q1 over Q1 as some kind of expansion. And then we put these numbers over here. Okay. So yeah. So but the issue is that this formula gets more complicated once, for example, once you add fourth leg, then suddenly you don't have these false theta functions. You have something more complicated. Yeah, but I have little time, so I want to talk about something. So I think it's not that hard to believe that if you do this formula for this kind of graph, you have one high valency vertex, which gives you some infinite series, then you have a bunch of these vertices, these leaves, which gives you the little bit sum of these three functions, and you just need to understand well what are these functions, and they are real. The point is that this formula is very complicated because it depends on this all data of the graph. But these manifolds can be written in a much easier way. So there should be a formula using just this much easier thing. And so this is this is like a still needs to be written as a conjecture. But I think this is very easy. It shouldn't be hard. And this is so first for cipher manifolds. So this first part should be easy. Cipher manifolds. Then if we take this Z0, so we take sum of all these guys, then there is a prefactor. And this prefactor should be related to Casson invariant, or at least seems to be for easy cases. So this should be something which depends truly on all these numbers P and Q. And what is the surprising part is that there is this series part. So something which starts with 1, and then there's some Q to some power of Q. Whatever, with some coefficients. And so the conjecture is that this, for cipher manifolds, only depends on this P1 up to Pn, and not on the Qs. And the way how it depends is that the right function. Okay, anyway, I don't want to go into this, but this is kind of surprising because in particular it says that for very different manifolds, because we have many, infinitely many manifolds with the same P's but different Q's. This series is actually the same up to up to this prefactor. And I forgot one thing, and this is the thing is that from these invariants you can compute the rank of H1, and when the H1 gets bigger, we need to scale this Q over here by the rank of H1. So there's like Q to 1 over H1. But otherwise, the series is just the same. So there is only this prefactor, and there is this scaling by H1, which is like the covering group, and then this is the same. So this is like this data for which you do the resurgence thing. So it tells you that two different manifolds are actually. Also, it tells you that the Wittmann-Reshetikhin interval are kind of related. I mean, they don't look the same because they are radial limits, so we multiply this by this stuff, which is different for the manifold. But all this Q series thing is just the same up to this scaling. Yes, and so once so I want to show you. Yeah. So this is the table in favor of Hikami. It's a Japanese mathematician which was trying to get generalized Lorentz and Xavier stuff for more examples, and he did it for his 14 Arnold unimodal singularities. But then he got into some struggles because it got really messy. But this was before these nice formulas were written, so now it's much easier. These were the examples which I was using to guess the formulas because they are very nice, and you can see all the phenomena. So these are the equations. Then these are the numbers over here. There is also some information on the Chern-Simons. This is so. For example, one thing which is cool is that there is some involution of these 14 singularities, and it preserves many things like the rank of H1, but it's not clear what happens with Chern-Simons. So this would be interesting. Yeah, but let me finish.
H1 is what?
H1 is the number of elements of the first. So if, once we have this, we can guess, like we'll do like a very wild conjecture, which says that this actually works for any graph manifolds. So for any graph manifolds, if and now I need to go back to the splicing. So having same P's and not Q's is pretty much related to this splicing, because this P. Sorry. I think I did prepare things for two talks actually. so anyway, there is a way how to write from the adjacency matrix. There is a way how to write an easier graph, which encodes only this splicing information, how we splice easier cipher pieces together. So this is called splicing graph, or splicing diagram. And so if we have integer homology spheres, then this just tells us how we splice together these cipher pieces, and it's unique. So it's very nice, and this is just a way how to describe the decomposition. But if you have Q homology spheres, then if you run the same construction, you will actually get something which can be the same for different manifolds. It's not unique. So there are different manifolds which have the same splicing diagram. And this corresponds to having the same piece over here. So you can have a wild conjecture that if two guys have the same splicing diagram, so you forget some information, this is still the same. Yeah. And so once we run the computer program, we get some examples which I can show you I should maybe write them on a board, but it seems I lost them. Anyway, there are examples of graphs like this. And then there is another one which is like, which has many vertices. Yeah, I can give you the numbers, but it's maybe not interesting. But this is very hard to compute, very hard to say anything about this, because now you have more valency vertices. And so this is one of these is say like homology sphere with 17 elements of H1. This one is homology sphere, and they have the same splicing diagram. Splicing diagram is like that you get rid of valency two vertices and you compute some determinants or subgraphs. And if you compute this invariant, you will actually get that the series is the same up to this scale, which is very surprising, and we have no idea why it is true and how to prove it. But maybe so one way is to try to rewrite this formula just in terms of this splicing graph. Other one would be try to prove some gluing formula when we splice things together. So yeah, so it started with this observation that these numbers play like an important role here. Then just a Qs, and then in the end it ended up with like that we can say the two series are the same, even though that we basically have no idea what are they, except that we can compute them explicitly on the computer. Yeah. Okay, so I think that's it.
Thank you very much. Are there questions? Maybe can you repeat what's the first conjecture?
Yeah, so the conjecture is that this, if we take this C0 invariant, then we can decompose it as a Q to some power, where this power should be some classical invariant of the three manifold, something like Casson invariant, Castle Walker in this case, and then there is an infinite series. So this is what is interesting, because there are these integral coefficients and the integral powers. So, and this part only depends on H1, but in a very simple way, not just on the rank of H1, and then on these cipher invariants. It can be said in a geometric way because the reason why Neumann and Wall started studying these splicing diagrams, that was all singularity theory. So that's kind of like the original motivation of quantum. So they were trying to construct the universal abelian covering, which is covering by this H1, and this you can actually get nice algebraic equations for the link of the singularity, which we see the link. It's like even though the equations always for like E6 singularity are kind of messy, if you do the universal abelian covering, you will get nice equations like this, of this diagonal Brieskorn type, or there should be 33 over here. So Neumann and Wall are puzzled why if you have a singularity with very ugly singularity with some link, and then you just do a covering of this manifold, then suddenly it's a link of a very nice singularity. And that's why they invented these splicing diagrams, because for example, they had a conjecture that Casson invariant is 1/8 of the Milnor fiber of the singularity, which proved to be wrong, but they found a class of singularities for which this is true. So this is all motivated, in a sense, this is in background all motivated by singularity theory. And this is also my motivation to relate it to singularities.
So you said the one for cipher manifold should be easy to prove?
I think so, because I have a conjectural explicit formula in terms of some kind of functions like this, and it works for all these cases in the table, so I think it works for all of them. And you just need to rewrite it, this thing. And I think basically this was already done in Bukov and Vanlasku's paper, but they somehow they didn't want to consider Q homology spheres, so they considered only Brieskorn spheres, which are of this form with PQR coprime, because they didn't want to care about these coefficients A, which appear here once you don't have homology sphere. But what I do here, I just sum them all. So I think basically the same arguments should work. And they also only considered 3 singular fibers, so you need to consider n singular fibers, and you need to adjust it. Yeah, but in the end, I think the answer is kind of simple. You know, it's like straightforward generalization of what they did in this case. This is much more surprising because it's like, yeah. Also, it's cool that there are now many directions. For example, these graphs. Not every splicing diagram is actually coming from a manifold. Maybe it's coming from some orbifold, or not even that. So once you have something which only depends on this, you can, I don't know, You can try to define for orbifolds. Yeah.
So maybe could us briefly remind how it's related to things which you told us in Sydney?
Yes.
This number look
that's
the same.
yes. And that's a good question. So yeah. So what I was talking in Sydney, I was talking about these numbers over here, and I said that they look the same as a spectrum of singularity of this universal abelian covered singularity. So that's you know, I was looking at these numbers, then I saw this is like I need to take this universal abelian cover, and then I got to this splicing business because this is all about the equations of the universal abelian covers. And now it's pure topology, pure topological statement, and there are no singularities. But how is it related? So I can write the formula for the cipher. So you know,
before you erase it, you put
sorry.
You put sum between the ZVs, because this V was so-called free variable.
Yes, you
So
integrate.
there was some not product.
There was like a multiple integral. There was a multiple
Oh,
integral over all these. Yeah. Sorry.
So product. Oh,
Yeah. Yeah, I was talking about this. It's really like taking a monomial in many variables.
There should be a gamma function, if I am not wrong. Remembers me. Recalls me. Reminds me of that. I don't remember. There is a famous formula for 1 over gamma.
I don't know.
Products and Z minus 1 over Z.
I'll check it out. Okay. So for the cipher manifolds, as I said, if you start taking these graphs, you need to do everything with these continued fractions, and the point should be that the continued fraction business is all hidden in here. Okay, and then you really just need to have something with the piece. So you write function like this, which is P is a product of all the P1, P2, Pn, and you take factors like this. Divided by all the Pns, and here you put x to P, x to minus P. I don't have so much evidence for this. I have evidence in 3 fibers and 1 example 4 fibers, because then people didn't do anything else. But it's so simple. It works. It goes well with the Kirby moves, because you can add one leg, right, and then just cancel something here, so it works. So I think it's just true. And then if you take this series, you expand it somehow similar to the way how you expand it, and then you just like instead of x to the n, you substitute q to the n squared over this 2p or something. I think you should get the series, and you should get actually C0 of q to the rank of h1. So I think this is also which most people are confused about, this is scaling of q here. Yes, I don't know how to get a formula for explicit for the z heads, because then you kind of, so the way how I think about it, I have this universal abelian cover. There is action of h1, which gives me the original manifold, and this stuff only depends on the covering, while this z heads, they really depend on the manifold downstairs. So you need to kind of incorporate how the action actually works. Yeah. Anyway, so this is the form. This is the function which appears there. You can also. This is like the function. if you exponentiate this variable, this is this Borel plane function in the resurgence business. And now, if you take a Poincare series of the algebra, which defines you the universal abelian cover, and this is in this case this is this is easy because this is just x to the p1 y to the p2 up to some c to the pn. And you need to consider n-2 equations. And you need to put some random coefficients over here, such that it's like a matrix with all the minors, non-zero or whatever. I mean, so that it's all transfer as well. So this is a complete intersection inverted n-2 equations. And if you look at the Poincare series of this, it's pretty much very similar to this thing, except that it's inverted, so this is upstairs, and there is just x e to the -1, and all these guys are here. Yes, and this is the Poincare series of the algebra, and this Poincare series should be related to the spectrum of the singularity by the theorem of Abelin. So even though now I'm not talking about the spectrum, but I'm talking about some Poincare series, at least in this ciphered case, it seems to be really like connected or like very, very similar. And I attended a talk of Andreas Nemeti in Miami like a few months ago, and he was saying, you know, for ciphered manifolds, and this corresponds to quasi-homogeneous singularities, all the invariants are the same. So in a sense, so it's like when you have something which is the same for these kind of, maybe it's too special to say something in general. So this is another thing which I need to think about now, because I kind of stopped doing singularity theory because I have now like topological statements, which can be proved maybe by topology, and yeah, but there should be, at least for the ciphered case, there should be a relation to singularity theory, and then it will be, of course, very interesting if there is a relation for more general. And I think this is like a hint that there actually should be a relation to singularity theory, at least from the point of view that like people were developing all this theory for singularities. Then maybe if it shows up here, then yeah. Okay.
Cool. By spectrum, yeah, you mean what?
I was talking about uncertainty. This is some eigenvalues of monodromy of the singularity, which defines you this.
So integrals.
So for example, this x squared plus y cubed plus z to the 5. You have also, if you take equals 0, then this is a singular surface. If you take equals epsilon, it's a smooth surface whose homology is a lattice of rank 8, which is the number of these vertices in the graph. And there is a monodromy operator, and you take the eigenvalues basically. So this is pretty much related to some roots of this Poincare series. But it's a tricky business because this relation of Poincare series with the spectrum is proved by considering case by case, because all the quasi-homogeneous singularities for surfaces were classified. So there is not much conceptual. I mean, maybe there is. I just don't know it. But, yeah.